Welcome! In this video, we'll explore the problem titled Maximum Split of Positive Even Integers. We'll go through the problem requirements, understand the challenges, and break down a solution step by step. Let's dive in. In this problem, we are given a positive integer called final sum, which represents the total sum we need to achieve using positive even integers. The goal is to split final sum into the maximum number of unique positive even integers such that their sum equals final sum. You can return these integers in any order, but if it's not possible to make the split, the output should be an empty array. To clarify, a positive even integer is any number greater than 0 that is divisible by 2. For the input, we are given a single integer, final sum, representing the target sum. The output will be a list of unique positive even integers that add up to final sum, or an empty array if the split is not possible. For example, if final sum is 12, the output could be 2, 4, 6. These are unique positive even integers, and their sum is 2 plus 4 plus 6, which equals 12. Now, consider a different case where final sum is 7. In this scenario, the output would be an empty array, as 7 is an odd number, and it is impossible to split an odd number into positive even integers. This highlights a key condition of the problem: if final sum is odd, it is not possible to generate a valid result. Another example is when final sum is 28. Here, one possible output is 2, 4, 6, 16. These integers are all unique, positive, and even. When we sum them, 2 plus 4 plus 6 plus 16 equals 28, which satisfies the condition. It's important to note that there may be other valid outputs as well, since the integers can be returned in any order. This flexibility allows for multiple correct solutions as long as the integers are unique, even, and their sum equals final sum. There are several edge cases to consider. First, if final sum is odd, such as 15, the output must be an empty array because it is impossible to split an odd number into positive even integers. Second, when final sum is very large, like 10 to the power of 10, the algorithm must be efficient enough to handle this without running into performance or memory issues. Third, the smallest even final sum is 2, and the only valid output in this case is 2. Finally, the output array must contain unique integers. For example, splitting final sum of 12 into 6, 6, would be invalid since the integers are not unique. These constraints ensure the solution is correct and adheres to the problem requirements. To start, let's consider the brute force approach. The main idea here is to generate all possible subsets of positive even integers and evaluate them to find which subset sums up to the given final sum. Once we identify all valid subsets, we would then select the one that contains the maximum number of unique values. The steps for this approach involve generating all subsets of even numbers, checking if their sum matches final sum, and selecting the subset with the most distinct elements. However, the computational complexity of this method is exponential. Generating all subsets alone takes 2 to the power of n, where n represents the even numbers considered, and checking the sum for each subset adds even more overhead. This makes the approach impractical for large values of final sum. While it might work for very small inputs, it's inefficient and not scalable for real-world use cases. Now, let's examine a much more efficient strategy, the greedy approach. The intuition here is to maximize the number of unique even integers by starting with the smallest even number, which is 2, and incrementally adding the next smallest even numbers until the sum either equals or exceeds final sum. The process begins by initializing a variable current to 2 and an empty list result to store the integers. While final sum is still greater than or equal to current, we subtract current from final sum and add it to result. Then, we increment current by 2 to move to the next smallest even number. If there's any leftover value in final sum after the loop ends, we add it as the final element since it will still be even. This approach is highly efficient, with a time complexity of O(n), where n is the number of terms added, and a space complexity of O(n) to store the result. It's simple, fast, and ensures that we achieve the maximum number of unique even integers. However, it's important to note that this approach assumes final sum is even, which the problem guarantees. There's an important realization that underpins this problem. The task is inherently greedy because the goal is to maximize the number of unique even integers, which is best achieved by starting from the smallest even number and adding consecutively larger ones. Skipping smaller numbers or deviating from this sequence would lead to fewer elements being used, making the solution suboptimal. Additionally, a key insight is that any leftover value at the end of the process can simply be added as the largest even integer, ensuring the sum remains correct. This observation simplifies the problem significantly. The greedy approach is the chosen strategy because it avoids the inefficiency of the brute force method and directly constructs the result in linear time. By iterating through even numbers sequentially, we guarantee that all elements in the result are unique and that their sum matches final sum. The method is both elegant and efficient, perfectly suited to the problem's constraints. While the assumption that final sum is even simplifies the approach, this is a valid condition given the problem guarantees. Finally, let's analyze the complexity of the greedy approach. The time complexity is O, sqrt, final sum, because the sum of the first k even numbers grows approximately with O, k squared, and k scales with the square root of final sum. Essentially, the number of terms added is proportional to the square root of final sum, making this method highly efficient for large inputs. The space complexity is similarly O, sqrt, final sum, since we store the resulting list of integers, which will contain roughly that many terms. This combination of linear construction, low computational overhead, and optimal usage of space makes the greedy approach the best choice for solving this problem. Its simplicity, efficiency, and ability to achieve the maximum number of unique even integers align perfectly with the problem's requirements. To solve this problem, we need to find a subset of positive even integers such that their sum equals a given target value, final sum. Importantly, among all possible subsets that meet this condition, we want to maximize the number of unique elements in the subset. To achieve this, we start by understanding the constraints. The input final sum specifies the exact target sum we must achieve, and the subset can only consist of positive even integers. Our objective is to maximize the cardinality of the subset, which means we want as many unique integers as possible. The first step in the algorithm is to generate a sequence of positive even integers starting from 2, such as 2, 4, 6, 8, and so on. We continue generating these numbers until the cumulative sum of the sequence exceeds final sum. For example, if final sum is 10, the sequence would include 2, 4, and 6 because their sum, 12, exceeds 10. This sets the foundation for constructing our subset in the next steps. Once we have our sequence of even numbers, we use a greedy algorithm to build the subset step by step. We start with the smallest even integer, which is 2, and add it to the subset. Then, we continue adding the next smallest even number, but only if the total sum of the subset does not exceed final sum. If adding the next integer would exceed final sum, we stop adding further numbers. For example, if final sum is 10, we begin with an empty subset and add 2, resulting in the subset 2, with a sum of 2. Next, we add 4, making the subset 2, 4, with a sum of 6. Adding 6 would exceed 10, so we stop at this point. Now, we need to handle any remaining sum. The difference between final sum and the current subset sum is calculated. If this difference is non-zero, we adjust the subset by replacing the largest element with a new value. Specifically, we add this difference to the largest element to ensure the subset sum matches final sum while maintaining the maximum number of unique elements. Using the same example, the subset 2, 4 has a sum of 6, leaving a remaining sum of 4. Replacing 4 with 8 gives us the final subset 2, 8 that satisfies all conditions. The last step in the algorithm is to validate the final subset and ensure it meets all requirements. We check that the sum of the subset equals final sum, and all elements are positive even integers. Once validated, we return the subset as the result. This approach is built on key insights. First, the greedy strategy of selecting the smallest available even integers ensures we maximize the number of elements in the subset before exceeding final sum. Second, if the greedy subset does not perfectly match final sum, adjusting the largest element allows us to meet the target sum without reducing the subset's cardinality. Finally, the algorithm is efficient because generating even numbers and constructing the subset involve linear operations, making the solution scalable for larger values of final sum. To implement this algorithm, we rely on simple and efficient data structures. A list is used to store the selected even integers, as it allows dynamic updates like adding new elements or replacing existing ones. Additionally, we use variables like current sum to track the total sum of the subset as it is being constructed, and remaining to calculate the difference between final sum and the current subset sum. The time complexity of the algorithm is driven by two main operations: generating even numbers and building the subset. Generating even numbers takes O, sqrt, final sum, as the sequence of even numbers grows quadratically. Constructing the subset also takes O, sqrt, final sum, since we iterate through the sequence of even numbers until the sum condition is met. The adjustment step, where we replace the largest element if needed, is an O1 operation. Overall, the algorithm runs in O, sqrt, final sum, making it both efficient and practical for this problem. This Python implementation solves LeetCode problem number 2178, maximum split of positive even integers. The goal is to split final sum into unique positive even integers such that their sum equals final sum while maximizing the count of integers. Explanation of the code. 1. Edge case check. The method first checks if final sum is odd. Since the problem requires splitting into even integers, an odd final sum is impossible to split, so it returns an empty list immediately. 2. Initialization. We initialize an empty list result to store the even integers and start with the smallest positive even integer current equals 2. 3. Greedy approach. The algorithm adds the smallest available even integer, current, to the result list. It then reduces final sum by the value of current and increments current by 2 to move to the next even integer. This continues as long as final sum is greater than or equal to current. 4. Adjust for remaining sum. If final sum is not 0 after the loop, it means we need to adjust the last added number in the result list to ensure the total sum equals the original final sum. This is done by adding the leftover final sum to the last number in the list. 5. Return result. The method returns the list of even integers that satisfy the conditions. Complexity analysis. Time complexity. The loop iterates through even numbers, and the number of iterations is proportional to the square root of final sum. Therefore, the time complexity is O, sqrt, final sum. Space complexity. The space used by the result list is proportional to the number of even integers added, which is also O, sqrt, final sum. This solution is efficient and ensures the maximum number of unique even integers are used to split final sum while satisfying the problem constraints. Here, we start by importing the necessary classes and defining our solution class. The method maximum even split takes a long integer final sum as input. The goal is to split this sum into the maximum number of distinct positive even integers. First, we handle a base case. If final sum is odd, it's not possible to split it into even integers, so we return an empty list immediately. Next, we initialize a list called result to store the even integers we find and set current to 2, which is the smallest positive even integer. The while loop is the core of our greedy approach. As long as final sum is greater than or equal to current, we add current to the result list, subtract it from final sum, and then increment current by 2 to move to the next smallest even number. This ensures that we are always adding the smallest possible even number, maximizing the number of distinct integers in the result. After the loop completes, we check if there is any remaining value in final sum. If there is, it means we couldn't exactly reach 0 with the distinct even numbers we added. To handle this, we take the last number in the result list and add the remaining final sum to it, ensuring the total sum matches the original input. This adjustment maintains the distinctness of all other numbers in the list. Finally, we return the result list, which contains the maximum number of distinct positive even integers that sum up to the given final sum. The method ends here, completing an efficient and clear solution to the problem. To solve this problem, we start by checking if the given final sum is odd or even. Since 12 is even, we can proceed with the solution. Next, we initialize two variables, result, an empty list that will store our split even integers, and current, which starts at 2, the smallest positive even integer. Now, we use a greedy approach to maximize the number of unique even integers in our result. First, we add current, which is 2, to the result list. This makes result equal to 2. We then subtract 2 from final sum, reducing it to 10, and increment current by 2, making it 4. In the next iteration, we repeat the process by adding 4 to result, resulting in 2, 4. We then subtract 4 from final sum, leaving us with 6, and increment current to 6. Finally, we add 6 to result, so it becomes 2, 4, 6. Subtracting 6 from final sum reduces it to 0, which means we've successfully split the sum into even integers. Since final sum is now 0, we can return the result, which is 2, 4, 6. Now, let's look at another example where final sum equals 28. Again, we check if final sum is odd, and since 28 is even, we proceed. We initialize result as an empty list and current as 2. Following the greedy approach, we add 2 to result, making it 2. We then subtract 2 from final sum, reducing it to 26, and increment current to 4. Next, we add 4 to result, so it becomes 2, 4. After subtracting 4 from final sum, it becomes 22, and we increment current to 6. We continue the greedy process by adding 6 to result, which now becomes 2, 4, 6. Subtracting 6 from final sum leaves us with 16, and we increment current to 8. Adding 8 to result makes it 2, 4, 6, 8, and subtracting 8 from final sum reduces it to 8. At this point, we increment current to 10, but since 10 exceeds the remaining final sum of 8, we adjust the last number in the result. Specifically, we add the remaining final sum of 8 to the last number in result, turning 8 into 16. This updates the result to 2, 4, 6, 16. With final sum now reduced to 0, we return the result, 2, 4, 6, 16. Finally, let's consider the case where final sum equals 7. Since 7 is an odd number, we know it's not possible to split it into even integers. Therefore, we immediately return an empty list. From these examples, we can make a few key observations. First, the solution uses a greedy algorithm to maximize the number of unique even integers in the result. By always adding the smallest available even number, we ensure that we efficiently use the final sum without wasting it on larger values prematurely. Additionally, if there's any leftover final sum after the greedy process, we add it to the last number in the result. This adjustment maintains the sum while ensuring that all numbers remain even. These principles make the solution both efficient and straightforward to implement. To analyze the time complexity of this solution, we break it down into 3 steps. First, the initial check to determine if final sum is odd involves a simple modulo operation, which takes constant time, 1. Next, we have the greedy loop, where we repeatedly subtract the current even number from final sum and append it to the result list. In each iteration, the value of current increases by 2, forming a sequence like 2, 4, 6, and so on. The sum of these numbers is bounded by final sum, and this sequence can be represented as an arithmetic progression. Using the formula for the sum of the first k terms, we find that the number of iterations, k, is approximately proportional to the square root of final sum, or O, sqrt, final sum. Finally, the adjustment step, where we add any remaining final sum to the last element in the result list, is a constant time operation, O1. The overall time complexity is therefore dominated by the greedy loop, making it O, sqrt, final sum. Now, for the space complexity, we consider the memory used by the solution. The primary contributor is the result list, which stores the even integers that sum up to the input final sum. In the worst case, the list contains k integers, where k is proportional to O, sqrt, final sum, as derived earlier. Each integer occupies constant space, so the total memory usage for the list is O, sqrt, final sum. Beyond this, the other variables such as current, final sum, and the loop controls occupy only constant space, or O1. Therefore, the overall space complexity of the solution is also O, sqrt, final sum. When comparing this greedy approach to a potential naive or brute force method, the efficiency becomes even more evident. A brute force solution might involve iterating through all possible combinations of even numbers up to final sum to find subsets that sum to the target. This process would involve an exponential number of operations, leading to a time complexity of O2 to the power of n, where n is the number of even integers less than or equal to final sum. In contrast, our greedy solution drastically reduces this to O, sqrt, final sum, by directly constructing the result list. Looking at different scenarios, in the best case, final sum is small, leading to fewer iterations and minimal runtime, though the time complexity remains O, sqrt, final sum. In the worst case, final sum is a large even number, requiring the maximum number of iterations. Finally, on average, the performance is consistently O, SQRT, final sum, with runtime depending on the magnitude of final sum rather than the input size. To provide a mathematical proof for the derived time complexity, let's revisit the behavior of the while loop. The loop iterates until the sum of the first k even numbers exceeds final sum. The sum of the first k even numbers is given by the formula k*, k plus 1. To determine k, we solve the inequality k*, k plus 1 equals final sum. Simplifying this inequality shows that k is proportional to the square root of final sum, or O, SQRT, final sum. During each iteration, operations like appending to a list, subtracting values, and incrementing variables all take constant time, O(1). Therefore, the total time complexity of the solution is O, SQRT, final sum. Similarly, the space complexity arises from the result list, which stores k integers, confirming that the space complexity is also O, SQRT, final sum. When tackling this problem, there are a few common mistakes to watch out for. First, many assume that maximizing the number of unique elements will always yield the optimal solution. While uniqueness is important, it's critical to ensure that the subset you construct also sums exactly to final sum. Over-prioritizing uniqueness without checking the sum can result in invalid subsets. Another frequent oversight is not properly accounting for edge cases involving final sum. For example, forgetting that final sum must be positive and even can lead to bugs. Cases like final sum equals 0 or odd values should be explicitly handled, as they are invalid inputs. Additionally, failing to consider smaller even numbers in the subset can lead to suboptimal solutions. For instance, with final sum equals 8, the subset 2, 6 is valid, but if you only consider 8, you're not maximizing the number of unique elements. Inefficient brute force approaches are another pitfall. Generating all possible subsets of even numbers up to final sum results in exponential time complexity. Instead, you should leverage arithmetic properties of even numbers for better efficiency. Lastly, it's critical to remember the goal of maximizing unique elements. If multiple subsets sum to final sum, you must choose the one with the highest number of distinct numbers. Overlooking this criterion can lead to incorrect results. Another mistake to avoid is skipping the validation of constraints. Always ensure that the numbers in your subset are distinct and that their sum exactly matches final sum. Neglecting these checks can lead to solutions that are invalid, even if they appear to work at first glance. Understanding the key pattern in this problem is essential. It revolves around two main principles. The subset must sum the final sum and have the maximum number of unique elements. A greedy approach is often effective here. Start with the smallest even numbers, like 2, 4, and 6, and iteratively add them to your subset, subtracting them from final sum as you go. This minimizes overlap and maximizes the number of elements. It's also important to pay attention to optimization. If you reach a point where the next even number exceeds the remainder of final sum, you may need to adjust. Watch out for edge cases as well. For instance, if final sum is 0, there's no solution since the problem requires positive integers. If final sum is odd, it's automatically invalid because even numbers cannot sum to an odd value. For small values of final sum, like 2 or 4, ensure your solution handles these minimal subsets correctly. This problem is closely related to several others on LeetCode that involve finding combinations or partitions. For example, in LeetCode 39, combination sum, the goal is to find all unique combinations of numbers that sum to a target. Similarly, LeetCode 40, combination sum 2, introduces constraints on duplicates, making it more challenging. LeetCode 90, subsets 2, focuses on generating all unique subsets from a list that includes duplicates, which is a slightly different variation. Finally, LeetCode 698, partition to k equal sum subsets, involves dividing an array into k subsets with equal sums, which has its own complexities. When thinking about alternative approaches to solve this problem, the greedy method is a good starting point. By starting with the smallest even numbers and adding them iteratively, you can efficiently build a subset that maximizes unique elements. However, you need to handle cases where the next even number exceeds final sum. This approach is computationally efficient, with a time complexity of O(n), but it may require careful adjustments to handle remainders properly. On the other hand, backtracking offers a more exhaustive solution. By exploring all possible combinations of even numbers, you can guarantee correctness. However, this comes at the cost of higher computational complexity, as backtracking has an exponential time complexity of 2 to the power of n. Another powerful approach to solve this problem is dynamic programming. With a DP table, you can keep track of achievable sums using distinct even numbers. This method strikes a balance between efficiency and correctness, as it avoids the brute force nature of backtracking while still ensuring that all constraints are met. However, it does require extra memory to store the DP table, which can be a trade-off depending on the problem size. By using dynamic programming, you can systematically build subsets that satisfy the conditions, ensuring that the sum equals final sum and the numbers remain distinct. While it may not be as fast as the greedy approach in simpler cases, it provides a robust and reliable solution for more complex inputs. Each of these methods, greedy, backtracking, and dynamic programming, has its strengths and weaknesses, so choosing the right one depends on the specific constraints and requirements of the problem you're solving. Great job! We've covered the key points of the problem maximum split of positive even integers. Remember to practice similar problems to strengthen your understanding and improve problem-solving skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!